Welcome to lecture 4. So in the last class, we were talking about second order tensors, and we are going to continue with that. Okay. We saw that linear transformations, there are tensors of first order, second order, third order, fourth order, and they're all linear transformations. Okay, and today we will talk more about second order tensors. Okay, before starting that, we have to fix some notation. Till now, we haven't really fixed any notation, so let us do that. So for a scalar, if a scalar will be denoted simply like this. Whereas if you have a vector, we will denote it with a bar below. Okay, and then if you have a second order tensor, we are going to denote it with 2 bars below. And for third order, then you have 3 bars, and likewise. In books, you will see that scalars are unbold, vectors are bold-faced, small letters, whereas second order tensors are bold-faced but capital letters. But when I write it, it is difficult to make it bold and unbold. So therefore, we will follow this notation when I'm writing with my own hands. Okay, so this is scalar. This becomes a vector with 1 bar below. Then this is a second order tensor. This is a third order tensor, and likewise. And vectors, you also know that they are first order tensors. And scalars, for example, are zeroth order tensors. Okay, and in the last class, we saw that any second order tensor, A, for example, can be written as Aij EI tensor product EJ, isn't it? And there is summation over I and J here, by the way. And Aij is called the component of the tensor A. So this is the component of tensor A relative to the basis EI tensor product EJ. Just like for vectors, we write that V is equal to VI EI, and VI is the component of V related to EI, isn't it? So for, yeah, please.
Sir, is there any physical significance of like component of tensor? Like for component of vectors, the physical significance is it is the projection onto that basis.
Yes.
But do we have something like that in tensor also?
So this is also a projection, but it's with vectors, you can relate it to physics that, okay, you are just projecting it along a direction. But with tensors, it is not easy to relate it through some physics. But mathematically, they are both projections. Components are always the projections, yes. And for vectors, the bases are E1, E2, E3. For second order tensors, the basis, so this is the basis. And there are 9 basis tensors here, isn't it? For every I and j, you get total of 9 basis tensors. And then we also saw that this Aij forms a matrix, isn't it? Which is the representation of tensor A in EI tensor product EJ basis tensors. Okay, and sometimes they also say that it is also the representation in E1, E2, E3 coordinate system. All right. We'll talk more about this representation later on. It is not so easy when it comes to tensors. There are several ways it can be represented. Of course, you can change the coordinate system and then the representation changes, but there are many more ways also, which we will discuss maybe by the end of this course, by the end of this class. All right. Okay. Now, how can we construct second order tensors? So construction of second order tensors. So suppose that we have this tensor big A, and we know how it acts on three vectors. So AE1 is equal to V1. And using index notation, we simply say that A into EI is equal to VI. Okay, for E1, E2, E3. So once we know how does this tensor act on three independent vectors, we would know how this is going to act on any arbitrary vector, isn't it? Because they are linear transformations, so you can find now for any arbitrary vector. So just by knowing this piece of information, is it possible for us to construct what exactly the A is? What is the form of A? Can we construct? So that is a question here. And you see, these E1, E2, E3, they need not be perpendicular to each other. They just have to be three linearly independent vectors. If you know how a tensor acts on three linearly independent vectors, then you can fully construct that tensor. So that way a tensor gets uniquely defined if you just know how it acts on three linearly independent vectors. And why I'm saying three? Because we are working in R3. If we are working in R4 or R5, then we have to think of 4 or 5 independent vectors. Okay, so let us see how do we construct the tensor. And keep in mind that E1, E2, E3, they need not be perpendicular.
Sir, can you tell this with example?
Yeah, of course. I mean, a very simple example is just think of E1 and then you have E2, which make an angle theta, and E3 is then coming out. So here the three vectors are not all perpendicular to each other, correct?
Right.
Okay. Also, they need not be unit vectors. The E1, E2, E3 need not be unit vectors also. For a second order tensor, you just need to know how it acts on three linearly independent vectors, which need not be either unit vector or perpendicular to each other. So if you just know that, then you can construct the tensor fully. Okay, so to construct the tensor, we are now going to introduce what is called dual vectors, or what is called dual basis. You see, this E1, E2, E3, because they are linearly independent, it also forms a basis for R3, isn't it? Any basis, any set of three linearly independent vectors can be the basis for R3. It does not have to be that IJK. It can be any set of three linearly independent vectors. So E1, E2, E3, for example, are any set of three linearly independent vectors, which can be a basis. Let me also write this here. Any set of three linearly independent vectors can be a basis for R3. Okay, and then for such basis we can talk of what is called dual basis also, and they are defined in the following way. So the dual basis has also got three vectors because it's also a basis. So it has also got three vectors denoted by E super 1, E super 2, and E super 3. Okay, and how these super and subscripts are related, how to relate these two. So it is given by the following formula. So E1, for example, is equal to E2 cross E3 divided by magnitude of E1 dot E2 cross E3. Okay, similarly, E2 is given by E3 cross E1 divided by magnitude of E1 dot E2 cross E3. And finally, E3 super 3 is given by E sub 1 cross product E sub 2 divided by magnitude of E1 dot E2 cross E3. What is so special about these dual bases? Try to find out E super 1 dot E sub 1 or E sub 1. Can you see what is this equal to?
Sir, can I?
Yeah,
Sir, the directional cosine between the.
of course, direction cosine. But looking at the definition of E super 1, what do you think it will be equal to? So just use this formula here. So E super 1 is this number over here, and I have to dot it with E1. So I get E2 cross E3 dot with E1 divided by E1 dot E2 cross E3. Okay, by the way, there is no magnitude sign in the denominator, so I have to remove this magnitude sign. I'm sorry. Because it's a right-handed, so we assume that E1, E2, E3 is forming a right-handed basis, so denominator by itself will be positive. Now, can you see what is this equal to? This E super 1 dot E sub 1?
1.
1, isn't it? So this is a nice property. Also see that if you try to do E super 1 dot E super 1, this is not equal to 1. Similarly, E sub 1 dot E sub 1, this is not equal to 1. Because as I still said to you, E1, E2, E3 are not unit vectors. Another interesting property is that when you do E super 1 dot with E sub 2, can you see what are you going to get?
0.
So just use a formula. Yes, you are right. So if you use the formula E2 cross E3 dot with E2 divided by that scalar product, and this automatically becomes 0. So you see, dual bases are such that you can finally write the following thing: E super I dot with E sub j is then equal to Kronecker delta super I sub j. So this is the same Kronecker delta. When I is equal to j, then it is 1, otherwise it is 0. Now you see it is such a nice property with bases which are not perpendicular to each other. So now you can't say that E sub I dot with E sub j. So this is not equal to delta ij. It is equal to delta ij only when E1, E2, E3 are unit normed and perpendicular to each other. But that is not the case always. But with dual bases in hand, you can always write this formula. So you can see the advantage of having a dual basis, isn't it? Well, you can't see, you'll see now what is the advantage. But they are really nice set of bases. I hope you are with me till now.
Yes.
Okay. Suppose that, well, maybe I can also give an example. So let me work out the example which I had drawn just above. So this is your E1 and say this is your E2. And for now, suppose that E1, E2, E3 are unit vectors, but not perpendicular to each other. So I have to make it unit vector. So I just make it look like that. So this is a specific example. Suppose E1, E2, E3 are unit vectors, but not perpendicular to each other. But yeah, E3 is perpendicular to E1 and E2. So E3 is coming out of the paper. So can you think of what will be the dual basis? What will be E super 1? Can you guess what is E super 1? So think of the formula. E super 1. That's E2 cross E3 divided by E sub 1 dot E2 cross E3. Now with this E1, E2, E3, what do you think? Where is E super 1? You can see that it is perpendicular to both E2 and E3. So where is it going to be? Do you think it is here? Is that correct?
Yes, sir.
Right. So, and then you will see that this angle is then 90 minus theta. And what is the magnitude of E super 1? The magnitude of E super 1, it is not equal to 1. What will this be equal to? See, you know that E super 1 dot with E sub 1, that has to be equal to 1. But the angle between them is 90 minus theta. So when you dot it, you get sine theta. So the magnitude of E super 1, it must be 1 by sine theta. Isn't it? Likewise, can you see where is E super 2? So E super 2 will now be perpendicular to E1, but in this plane itself. So E super 2 is going to be like this. And again, this angle is 90 minus theta. And what is the magnitude of E super 2? That's also 1 by sine theta. And you'll also see that E super 3 is simply equal to E sub 3. Okay, I hope you are with me here. Now suppose, I want to express a vector in terms of its components. So we have read till now that a vector V is equal to VI EI, isn't it? Where VI is equal to V dot EI. But this works, so this works only if E1, E2, E3 are what is called orthonormal. See, ortho means perpendicular to each other and normal means normalized. So E1, E2, E3 are unit vectors and perpendicular to each other. So this thing works only if E1, E2, E3 are orthonormal. And in fact, when you have orthonormal basis, then dual basis coincides with the original basis. So I can make that remark here. Dual basis coincides with original basis if the original basis is orthonormal. Can you see that here, that it is going to be the case? From formula, for example, you see in this formula, if E2 and E3 are perpendicular, then their cross product will automatically be along E sub 1, right? And also this scalar product in the denominator by default will be 1 if E1, E2, E3 are unit normed and perpendicular to each other. So E super 1 becomes equal to E sub 1. And likewise for E super 2 and E sub 2. Okay? So anyway, coming back to a general basis. So what I'm saying is this thing does not work always. But with the introduction of dual basis, we can write the following: V equal to V super I E sub I, where V super I is the component of the vector along the dual basis. So now you can write this. And this works for any basis. This works for any basis, E1, E2, E3. Can we check that indeed that is the case? For example, when you, let's say when I dot this V with E super J, I have to get what? From this definition, I should get V super J, isn't it? Now see if I use this, am I getting it? So you have V super I E sub I dot with E sub J. So this becomes V super I EI dot with E super J, which is equal to VI delta IJ. And because of Kronecker delta, summation over I will be gone and I will be replaced with J. And you see, this is what I wanted. So this should be indeed equal to V super J, and this is what you're getting also. So you see, this is the advantage of having dual bases, that you are still able to write V as VIEI. So you can still write V as VIEI, but then VI is the component along the dual basis. Okay, you can't write it as V sub IEI. This is not correct. You can write it also as V sub I but E super I. So here V super I is V dot E super I, and here V sub I is V dot E sub I. Okay, so basically the middle one is not correct. So with dual basis, you can write exactly as if it were the ordinary basis. So the indicial notation works perfectly. So can you see the advantage of dual basis now?
When you write delta ij, where j is above, I is down.
Yes.
So it has to follow the same, like whichever index is down,
Yeah,
that will go down.
correct, correct. Yeah, that's a
And
very good question. Now we are working with superscript and subscript. Earlier, we are only working with subscripts.
yes,
But with bases which are not perpendicular to each other, we have to now differentiate between superscript and subscript. Okay, because superscripts are the components along the dual basis. Okay,
okay.
so this one has to do this when you have curvilinear coordinate system. We have been working with Cartesian coordinate system where the basis vectors are orthonormal. But when you have curvilinear coordinate system where the basis vectors need not be orthonormal, then this thing will be really useful. Okay, I hope you get the point.
Yes. Sir, if I is above, j is below, then how it will operate in the line, which is the first line, which is currently showing on the right side?
Please say again what is?
V, if instead of V superscript I delta superscript j subscript I, we have V superscript I delta superscript I subscript j.
Okay, that is not allowed. So you see, with curvilinear coordinate system, the whenever you have an index repeating, then those repeating indices, one should be in the superscript and the other one should be in the subscript.
Okay, then only it works.
Yes, then only it works. So you have to always make it like this. The repeating index should be such that one of them appears as superscript and the other one appears as subscript. So let me make that remark here. That was a very good question. So repeating indices should be written such that one of them appears as superscript and the other one as subscript. See, with orthonormal basis, this does not matter. Everything becomes a subscript with orthonormal basis. But when you don't have orthonormal basis, then you have to do this way. Okay, coming back to finding out, constructing the second order tensor. So our original problem was that we know A into EI, that's equal to VI. So then what is A? What is A equal to? That is the question.
Sir,
Can you now think of what will A be equal to? Any guesses? What can A be equal to? Well, I think it's a difficult question at this stage. So let me just write down the answer and then we can also verify. So A is simply going to be equal to V sub I tensor product E super I. That's your second order tensor, very simple. So once you know how A is acting on three linearly independent vectors, you can construct your second order tensor with this formula. And you can also cross check. For example, cross check what is A into EJ? It should be VJ, right? Let us see, are you getting this? So A into EJ is VI tensor product E super I into EJ. But we know that with this spatial second order tensor, these two get dotted. This simply gives me V sub I product IJ, what it should be. Okay, so you can see that it is so easy to construct second order tensor once you have dual basis with you. All right. Okay. Then we have some more interesting questions. Okay, before going there, I can just introduce some more formulas. Some interesting formulas. So first one is that A tensor product B, if you have a tensor like this and you want its transpose, then it is simply B tensor product A. Can you prove this, that it is going to be the case? See, the proof is also quite simple. So suppose so I'm just going to write here, suppose big A is equal to A tensor product B. Then you remember the transpose definition. It was that A into X dot with I, and if you bring X on the other side, then it has to become transpose. That's how transpose is defined. So we just have to see that the above transpose formula satisfies this identity. If it does, then our formula is correct. So put on the left hand side your A. So what you have is A tensor product B into X dot with Y. So this becomes A dot Y into B dot X, isn't it? Now look at the right hand side. This is now X dot A transpose, we said it is B tensor product A, and then you multiply with Y. So what you get is X dot B into A dot Y, and you can see both are same. So this proves our formula here. Okay. Then the other thing is, when you have two tensors of this kind and they are just being multiplied together, okay, then we define it. So this is now a definition. It is not to be proved. This is just a definition. This is how two tensors multiply together. So we are simply going to dot the inner ones, okay, and then this becomes A tensor product D of B dot C. Okay, so I'll write here that this is definition for multiplication of two second order tensors. All right. Sometimes this is also called single contraction. So this formula, this is also called single contraction. And therefore, at many places, you will see it is written like this: A tensor product B, and there will be a single dot for single contraction. Then there is also what is called double contraction. So this is tensor product. So in case of double contraction, the definition is the following. So double contraction is written like this, with a colon. And the definition is A dot C into B dot D. So that's the definition. Okay, and we call it double contraction. Double because two of the vectors have been contracted. You see there is one contraction and another contraction here. So therefore it becomes a double contraction. In case of single contraction, there was just one contraction here. Okay, so this is just a definition. There is nothing to prove here. But finally, you have something to be proved. So I can write here to prove um, Yeah. So can we prove this? What do you think? Can we prove this? So you see, when if it were, it's not like A gets multiplied with both of them. So this is not true. Don't make this mistake. So this is not correct. So yeah, we can prove this, and let us see the proof. So this big A is any general second order tensor. So we can write it as Aij Ei tensor product Ej. Okay, because it's a general tensor, you can always write it like this. And then it has to be multiplied with A tensor product B. Okay. Now we just learned how two second order tensors multiply. The inner one gets dotted. So this becomes Aij Ei Ej dot A, right? Okay, maybe I have to put this EI afterwards. And then it is EI tensor product B. Okay. So what do you think? What is this now? So any idea how we can prove this? So I also have to think about it. It's not so trivial now. Okay, maybe I should write it slightly differently. So this is basically Ej dot with A, of course, into Ei, and then you have tensor product B, correct? Now, can we show that this thing over here is AA? Can we show that? If we can show that, then that will be the proof.
Sir,
Yes?
delta kind of thing.
Delta? Say again?
Delta ij? No.
But where do I use delta ij? Maybe, you can also, because you know the answer, AA, what is this equal to? This is again Aij, EI tensor product EJ, correct? Into A. But what is this? We learned how such tensors multiply, isn't it? So this is simply Aij Ej dot A into EI. And you see, this is what it is exactly. So this is what it is written here. And therefore, this becomes AA tensor product B. What do you think? Is that fine? The other way, now that I see that I could work it out, you could have also come directly from here. You see, you could work it out as, so I could have written this as Aij Ei Ej dot A, isn't it? This is what it is. But then this is also equal to Aij Ei tensor product Ej multiplied with A. Isn't it? That's the definition when a second order tensor multiplies with A. And then this is equal to this scalar you can bring inside the bracket, which is now A into A. Okay, so this is how we prove it. Likewise, there's another identity, which is that, did I already write it ever, or, okay, no, I haven't written. So it is that E tensor product B multiplied with A, but on the right, this is equal to A tensor product A transpose B. So can we prove this? So again, you can go in the same way as you went ever. So this is equal to A tensor product B multiplied with Aij of Ei tensor product Ej. Correct? So you have two second order tensors multiplying, and then you know how it works. It is simply A, and then you have inside the bracket Aij B dot Ei, and then you have tensor product Ej. Isn't it? Because the inner ones have to be dotted, and they're B dot Ei. Okay, I hope you are getting it. See, when you dot the inner ones, you are left with two tensor product here, two of them. But there is no meaning of two of them now, because you have a scalar thing now, and so one of the tensor product goes away, and therefore only one remains here. Anyway, so now see, can we do something? So this is also equal to A tensor product Aij B dot Ei Ej. So I brought this scalar thing on the other side of tensor product, because scalars can be moved anywhere. You see, you can't move vectors anywhere. The vectors or tensors have to be in the same sequence. But scalars, you can move anywhere in the expression. So now, can we say something now? Okay, you see, this is now also equal to A tensor product Aij Ej into B dot Ei. See, this is also perfectly fine. So I just moved the scalar after Ej. So as I told you, scalars can be moved wherever you want. Now, you see, this is now same as A tensor product Aij Ej tensor product Ei multiplied with B, isn't it? Because, by the definition, these two are dotted, and therefore you get B dot Ei. Okay, so this is finally A tensor product. Aij, Ej tensor product Ei into B. And can you see what is this thing inside the bracket? So your tensor A was Aij, Ei tensor product Ej. But what we have here is Aij, Ej tensor product Ei. That has to be A transpose, isn't it? So what you get finally is A tensor product A transpose B. And this is what you had to prove. Okay, I hope you got it. Any question till now? No question? Okay. So this covers our chapter 2 from that book. And we actually did something more. We also did this dual basis. Dual basis is not there in chapter 2. But there is, of course, there are a lot of things in chapter 2 which we did not do. But I will like that you guys go through the entire chapter 2. Because some of them, whatever I didn't do, suddenly you will do that in engineering mathematics. And those of you who have not taken engineering mathematics, you should certainly know them. Okay? So please revise chapter 2. And there are solved examples. Work out all these solved examples. So when we meet on Monday next week, you should have done this. You have revised entire chapter 2 and worked out all these solved examples. It is already worked out. You just have to go through the solved example. So I should write go through all the solved examples.